There is a hole in the moon. Not a crater, not a scar from an ancient impact. A hole that goes straight down, vertical walls, a floor 105 meters below the surface. And at the bottom of that hole, in the darkness beyond where the sunlight can reach, there is an opening, a door, into something that has been sealed since before the first fish appeared in Earth's oceans. The floor of that cave sits at approximately 17 degrees Celsius, not the temperature of a machine or a controlled environment, the temperature of a world that has found its own equilibrium in the dark, steady, constant, varying by less than 1 degree over an entire lunar day, while the surface above swings through 300 degrees of thermal violence. Somewhere beneath the ancient volcanic plains of the moon, there are tunnels, long hollow passages formed when rivers of lava drained out from beneath their own hardened crust 3 billion years ago, leaving behind caverns wide enough to contain a city. Some of them may stretch for hundreds of kilometers. Some of them may have ceilings thick enough to block every form of harmful radiation the universe sends toward the moon's surface. Some of them have never been touched by light of any kind. Not sunlight, not starlight, not the light from any instrument human beings have ever built. Tonight, you are going into one, down through the vertical shaft of a pit that NASA's Lunar Reconnaissance Orbiter confirmed with radar in 2024, down past the boundary where the surface temperature stops being relevant and the cave temperature takes over, into a passage in the dark basalt that has been waiting unchanged for 3 billion years. You will feel the walls with your hands. You will stand in a temperature that ancient physics has been quietly maintaining since before the Cambrian explosion. You will be inside the moon. This is quiet science at bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in this story comes from real scientific research and observation. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. The moon did not always look the way it looks tonight. The face that turns toward Earth, the one you have seen your entire life, the one that has been looked at and named and mapped since before recorded history, is not the face the moon was born with. The pale gray highlands, the dark patches of the Maria, the scattered craters that cover everything. This is the result of billions of years of geological work, of a world that was once violently, completely alive with volcanic fire, and that carried that fire long enough to leave behind something extraordinary in its interior before finally going still. To understand what waits in the cave you are going to enter tonight, you need to understand what the moon was doing 3 billion years ago. The moon formed approximately 4.5 billion years ago in the aftermath of a collision between the early Earth and a Mars-sized body. In the heat of that formation, the entire outer portion of the moon was molten, a global magma ocean covering the surface to depths of hundreds of kilometers. As that ocean cooled over tens of millions of years, lighter minerals floated upward and formed the pale highland crust you can see today. Heavier minerals sank, the interior differentiated into layers. And then, hundreds of millions of years later, the heat still trapped in those interior layers began to work its way outward. Partial melting occurred deep in the lunar mantle, at depths between 200 and 400 kilometers, at temperatures around 1200 degrees Celsius. Magma formed. It was less dense than the solid rock surrounding it, and buoyancy drove it upward through fractures in the crust. It reached the surface and poured out, not explosively, the way a stratovolcano erupts on Earth, but fluidly, in vast low-viscosity floods of basaltic lava that spread across the floors of ancient impact basins and filled them layer by layer, flow by flow, over hundreds of millions of years. The dark plains you can see from Earth with the naked eye, the Mare, the so-called seas that are not seas at all, are the result of this flooding. Mare Tranquillitatis, the Sea of Tranquility, where Apollo 11 landed in 1969. Mare Imbrium, Oceanus Procellarum. These are ancient lava plains built up from overlapping eruptions that occurred primarily between 3.9 and 3.1 billion years ago, with the most intense activity concentrated in two major pulses that the Apollo rock samples and subsequent isotopic dating have pinned down with increasing precision. The Chang'e 5 mission, which returned samples from Oceanus Procellarum in 2020, pushed the known extent of lunar volcanism further than any previous data. Basalt samples dated to exactly 2 billion and 30 million years ago. 2 billion years. At that point in Earth's history, the atmosphere was just beginning to accumulate free oxygen. The first eukaryotic cells had barely appeared, and on the moon, lava was still flowing. Mare volcanism on the moon lasted for at least 2.5 billion years. 2.5 billion years of eruptions, large and small, building up the dark plains one lava flow at a time. And as those flows moved across the lunar landscape, not as discrete events, but as sustained rivers of molten rock, channeling across the surface for kilometers, sometimes tens of kilometers, something happened in the physics of how lava cools that created the spaces you are going to enter tonight. The surface of a lava flow cools first. When molten basalt reaches the surface and begins to move across the landscape, it is exposed to the vacuum of the moon, a vacuum that radiates heat away efficiently, cooling the outer skin of the flow faster than the interior. The crust that forms on the surface insulates the still molten rock below it. The lava continues to flow, channeled now beneath its own hardened roof, moving through the interior of what is essentially a self-made tunnel. When the eruption eventually slows or stops, the molten material inside drains away, downslope, following whatever gradient the terrain provides, leaving behind a hollow tube. A lava tube? On Earth, lava tubes form in the same way, in Hawaii, in Iceland, and the Canary Islands, wherever basaltic lava flows across sloped terrain. The tubes on Earth are impressive. Some extend for tens of kilometers. Some are wide enough that you could walk through them upright without difficulty. The famous Kazumura Cave on Hawaii's Big Island is more than 65 kilometers long, making it the longest and deepest known lava tube on Earth. But the moon's gravity changes everything. Earth's gravitational acceleration at the surface is 9.8 meters per second squared. The moon's is 1.62, about 1/6 of Earth's. This lower gravity means lower stress on the walls and ceiling of a lava tube as it forms and as it sits over geological time. On Earth, the weight of the rock above a cave exerts pressure on its walls. There is a limit to how wide a passage can be before the ceiling collapses under its own weight at Earth's gravity. On the moon, that limit is dramatically higher. Theoretical modeling and gravitational data from the Grail mission, a pair of spacecraft that mapped the moon's gravity field with extraordinary precision between 2011 and 2012, suggest that lunar lava tubes could be as wide as 1 kilometer while still remaining structurally stable. Some models suggest tubes up to several kilometers wide are possible with sufficient sealing thickness. The Lunar Reconnaissance Orbiter has imaged over 200 pits on the moon's surface, circular holes ranging from 5 meters to more than 900 meters in diameter, many of which are thought to be skylights, where the ceiling of a lava tube has locally collapsed, opening a window into the passage below. 200 known windows into the subsurface. And below each one, if the models are correct, a passage that may extend far beyond what the skylight reveals. Tonight, you are going to descend through one of them. You are standing on the surface of Mare Tranquillitatis. The name means Sea of Tranquility, and from Earth it looks like a sea, a broad, dark, relatively smooth plain near the center of the moon's near side, visible to the naked eye as one of the large dark patches that give the full moon its familiar face. But there is no water here. There has never been water on this surface. What you are standing on is basalt, dark, fine-grained volcanic rock formed when ancient lava cooled quickly at the surface, its texture determined by the speed of that cooling, its composition a record of the chemistry of the lunar mantle, from which the magma rose 3.5 billion years ago. The ground beneath your boots has a texture unlike any rock on Earth. It is covered in regolith, the powdery broken layer produced by billions of years of micrometeorite impacts, grinding the surface rock into a range of particle sizes, from fine dust to small fragments. The regolith here is dark gray, slightly cohesive when compressed, and it holds the impressions of your boots with perfect fidelity. If you pressed your hand into it and lifted it away, the print would remain. In the absence of wind, in the absence of any erosive force, it would remain for millions of years. It is mid-lunar day right now. This matters enormously because the moon experiences one of the most extreme thermal environments of any solid surface in the inner solar system. A lunar day lasts approximately 29.5 Earth days, the same period as the moon's orbit around Earth, because the moon is tidally locked and rotates once for every orbit. During the approximately 2 weeks of lunar daytime, the surface exposed to the sun heats to approximately 127 degrees Celsius. During the approximately 2 weeks of lunar night, without any atmosphere to retain heat, the surface cools to approximately -173 degrees Celsius. 300 degrees of thermal swing every single month for 4.5 billion years. The surface you are standing on right now is approximately 120 degrees Celsius in the direct sunlight. Your suit is managing this. Its thermal control systems are radiating the excess heat away, maintaining the interior at a comfortable temperature. But if you pressed an unprotected hand against the surface rock, it would blister in moments. The rock itself does not glow or smoke. It simply radiates heat silently into the vacuum, a surface baked by unfiltered solar radiation with no atmosphere to moderate or soften it. The sun here is not the soft disk you see from Earth. Without atmospheric scattering, it is a point of incandescent intensity, visually small but energetically overwhelming. Its light arrives at the moon at the same solar constant as it arrives at the top of Earth's atmosphere, approximately 1,360 watts per square meter. But here there is nothing to absorb or scatter it before it reaches the surface. The shadows it casts are absolute. There are no partial shadows here, no penumbra softened by atmospheric diffusion. Every shadow is a sharp, geometrically precise edge between full illumination and complete darkness. You are looking at one of those shadows now. Approximately 40 meters ahead of you, the flat surface of Mare Tranquillitatis simply ends. There is no crater rim, no buildup of ejecta to warn you. The ground continues to where you are standing, and then there is an edge, and beyond that edge there is nothing, a vertical drop into darkness. The pit. You approach it carefully. The edge is not fragile in the way that cliff edges on Earth can be fragile, undercut by water, softened by weathering, crumbling under the weight of approaching footsteps. This edge is basalt, dry, cold beneath its sun-heated surface, unchanged in its structure, since the ceiling of the lava tube below it collapsed inward some unknown number of millions of years ago. You approach to within 2 meters of the edge and stop. The pit is roughly circular. The Lunar Reconnaissance Orbiter's high-resolution camera has measured its outer diameter at between 140 and 146 meters, approximately the width of 2 American football fields, placed end to end. The inner pit, the deep vertical portion below the sloping entrance funnel, is between 88 and 100 meters across. The walls are vertical, or very nearly so. The radar imaging published in Nature Astronomy in July of 2024 by researchers at the University of Trento confirmed what the optical images suggested. This is not a gradual bowl, but a genuine pit with overhanging or vertical walls reaching downward into the basalt. The total depth from the surface to the floor is approximately 105 meters. You look down. In the direct sunlight that reaches part of the floor, the portion not shaded by the pit walls, the regolith at the bottom is the same dark gray as the surface around you. Scattered boulders, a rough texture, a floor that no spacecraft has landed on and no human being has ever seen in person. The floor is approximately the width of a large building's interior, and it is in the portions that the sun cannot reach, dark with a quality of darkness that is different from the darkness you experience in a room with the lights off. There is no ambient light here, no light bouncing off walls or ceilings, no atmospheric glow, no distant streetlight through a window. The parts of the pit floor in shadow are in a darkness that is optically complete. And at the western side of the floor, where the pit's geometry creates a permanent shadow and the radar data showed the strongest anomalous reflections, there is the opening. You cannot see it clearly from up here. The angle is wrong, the distance too great, the shadow too deep, but the radar data showed it unambiguously, a void tens of meters in size, beginning at the western wall and extending horizontally into the basalt beyond the pit floor, a cave conduit, an accessible passage into the lava tube system beneath Mare Tranquillitatis. 41 years before you were born, humans landed approximately 400 kilometers from where you are standing. They collected rocks and deployed instruments and looked up at an Earth that did not move in the sky above them. They did not know this pit existed. The instruments that would eventually find it, the LRO camera, the mini RF radar, had not yet been conceived. Now the pit is known, and you are here. You attach the descent line to an anchor set into the regolith 2 meters back from the edge. The anchor holds well. The regolith here, compacted by billions of years of micrometeorite gardening, is more cohesive at depth than its surface texture suggests. You check the attachment 3 times. Then you step back to the edge, face the surface, and begin to back over it. The pit walls are close on both sides as you lower yourself below the rim. The basalt here is dark, darker than the surface regolith above, less processed by micrometeorite impacts, more of the original volcanic texture preserved. You can see where different lava flows have layered one on top of another over the course of the mare's formation history. Horizontal lines in the rock where one eruption ended and another began, each flow perhaps 10 to 20 meters thick, stacked like pages in a geological record that covers hundreds of millions of years of lunar volcanic history. You descend slowly. At 10 meters below the rim, the character of the light changes. The direct sunlight that floods the surface above cannot reach the pit walls at this depth. The geometry of the pit means that the sun's low-angle rays are blocked by the opposite wall before they can illuminate where you are. The light reaching you now is indirect, reflected from the sunlit portions of the pit floor below, bounced upward and sideways in a diffuse gray glow that is enough to see by but not enough to cast shadows. It has the quality of light inside a concrete room with no windows, where everything is visible but nothing has color or direction. At 30 meters, the temperature begins to change. Not through any physical contact, you cannot feel the ambient temperature through your suit's insulation, but your suit's external sensors register it, and the data appears in the corner of your visor. The surface above you is at 123 degrees Celsius. The pit wall at your current depth is at 61 degrees. By the time you reach the floor, the data shows it will be at approximately 17 degrees. The physics of this temperature gradient is precise and well understood. The sun's energy reaches the lunar surface as radiation, electromagnetic energy traveling at the speed of light, arriving at the surface, being absorbed by the dark basalt, and re-emitted as infrared heat. Everything above ground is subject to this energy input. But the pit walls below a certain depth are shielded by the geometry of the pit itself. The sun cannot illuminate them directly, and the indirect radiation that does reach them is insufficient to significantly heat the rock. The rock at depth, instead, radiates what heat it has outward toward the cold vacuum of space at night, cooling toward a temperature determined not by the sun, but by the average of all the energy inputs available to it in the pit's geometry. That average is 17 degrees Celsius. The Diviner Lunar Radiometer experiment aboard the LRO measured this in data published in 2022. Temperatures within the permanently shadowed portions of the Mare Tranquillitatis pit, fluctuating minimally around 17 degrees Celsius throughout the lunar day. The measurement varied by less than 1 degree Celsius over the course of an entire month. 1 degree of variation over a month, while the surface above swings through 300. You continue to descend. At 60 meters, you pass below the depth at which any direct sunlight has ever reached in the history of this pit. From this point down to the floor and into the cave beyond, you're in an environment that has been thermally isolated from the sun for as long as this pit has existed, potentially millions of years, potentially much longer, as some pits are thought to have formed during the final stages of mare volcanism billions of years ago. The walls here are unmarked by the thermal cycling that has slowly fractured and abraded the surface above. The basalt is solid, coherent. You can see the layering more clearly now, the stratigraphy of the mare's formation, each horizontal band a separate eruption, each eruption separated from the next by an interval of geological time, during which the surface was quiet and the next pulse of magma was building pressure in the depths below. The lowest visible layer, the one closest to the floor of the pit, the one that represents the oldest eruption exposed here, is approximately 3.5 billion years old. You descend through 3.5 billion years of geological time in 100 meters. At 90 meters, the floor is close. The gray glow of reflected light is less uniform down here. Most of the illumination is coming from the sunlit patch on the eastern side of the pit floor, and its light reaches the western wall only as a faint secondary reflection. You slow your descent and let your eyes adjust. The floor comes up under your boots gradually. You release the tension on the line and stand. The regolith here is finer than on the surface above, less processed by recent micrometeorite impacts. The pit's geometry intercepts most of the incoming debris before it can reach the floor. It retains more of the original fine-grained texture of the basalt, weathered over long timescales, rather than battered by repeated high-velocity impacts. It compresses slightly under your weight and holds your impression perfectly. You are standing on a surface that no human being has ever stood on. No spacecraft has landed here. No sample has been taken from this floor. The orbital cameras have imaged it from above. The radar has probed through it, but no physical contact has been made between a human-made object and this regolith. You turn toward the western wall. The opening is there. In the shadow cast by the pit wall above, where no light has reached since this pit first opened, there is a gap in the basalt at the base of the wall. It is roughly the width of a large doorway at its most accessible point, though the radar data suggests it expands beyond that as it extends deeper into the rock. The edges of the opening are the same dark basalt as the surrounding wall. No special marking, no dramatic framing, just a place where the rock ends and the darkness begins. The cave entrance. You check your suit systems, life support nominal, lighting operational, communication link to the relay in orbit confirmed. You activate the helmet lamp. A cone of white light appears in the darkness. It catches the basalt walls of the passage beyond the entrance. The rock is dark gray, fine-grained, smooth in places where the original lava flow surface cooled quickly and preserved its texture, rougher in others where subsequent fracturing has exposed fresher surfaces. About 2 meters from the entrance, on the left wall at approximately knee height, a thin protrusion of darker rock juts inward, a lavasicle formed when a small amount of lava dripped from the ceiling during the cooling of the tube and solidified before it fell. It has been there for 3 billion years. The passage beyond extends into the dark beyond what your helmet lamp can reach. Your suit reads 17.3 degrees Celsius. You breathe. In. Out. And you step inside. The first thing you notice is the quality of the silence. You have been in silence since you stepped out of your landing vehicle onto the surface of Mare Tranquillitatis. The moon has no atmosphere, and without atmosphere there is no medium through which sound can travel. You have heard nothing since your arrival except the mechanical sounds transmitted through the structure of your suit. The hum of the life support system, the faint click of suit systems cycling. But there is something about the silence inside the cave that is different from the silence on the surface above. On the surface, the silence is open. It extends in all directions, upward into the vacuum of space, outward across the flat plane of the mare, inward beneath your feet, to whatever depth the regolith reaches before solid basalt begins. It is a silence without walls. It has no boundary except the limits of the vacuum itself. Inside the cave, the silence has shape. The basalt walls on either side of you, the ceiling above, the floor beneath, they define a contained space, and within that contained space, The silence feels different in a way that is not a physical property of the sound, but a human response to geometry. You are enclosed. The silence here is bounded. It belongs to this space in a way that the surface silence does not belong to any space, because the surface has no shape to belong to. You walk slowly along the passage. Your helmet lamp illuminates a circle of floor and walls approximately 4 meters across. Beyond that circle, the darkness is complete. Not the darkness of a room where your eyes are simply unadjusted. Absolute darkness, optical darkness, the darkness of a space where no photon has arrived in 3 billion years, except for the ones your lamp is introducing right now. The cave is wider than the entrance suggested. Within 15 meters of entering, the walls have moved apart. The passage is now perhaps 6 or 7 meters across at its widest point, and the ceiling, visible in the upper range of your lamp's beam, is approximately 4 meters above the floor. This is consistent with the kind of lava tube that forms at the distal end of a long flow, where the tube has partially drained and the geometry has settled into a stable cross-section that the cooling rock can sustain indefinitely against the moon's gravity. The walls are layered. You stop and look at the left wall. In the circle of your lamp, you can see 3 distinct bands of basalt, each slightly different in texture and color. Not dramatically different because the variation in Mare basalt composition is subtle, but distinguishable once your eyes have adjusted to the scale of the differences. The lowest band is the oldest, the floor of the original lava tube, the surface on which the last lava drained away when the eruption that formed this passage ended. Above it, a layer of slightly different grain size and slight color variation, a later flow that partially filled the tube before it too drained, leaving its own mark on the walls. Above that, the ceiling rock itself, the original crust of the flow, the material that hardened first and formed the roof under which the molten lava channeled. 3 moments in the history of the moon's volcanic life, preserved in a sequence of layers you can trace with your gloved finger. You reach out and touch the lowest layer. The rock is cold beneath your glove. Not dramatically cold, your suit insulates you from it, but the sensor in your fingertip registers the temperature of the contact surface. Approximately 17 degrees Celsius, the same as the air temperature in this cave, the same as it has been for as long as this space has been enclosed from the surface above. This rock cooled from magma at approximately 1200 degrees Celsius. It cooled at the rate determined by the thermal properties of basalt and the geometry of the tube it was forming. Quickly at the surface where the vacuum drew heat away, more slowly at depth. When it reached its final temperature and stopped contracting, it locked into place, and it has remained at approximately this temperature, this specific, unremarkable, comfortable 17 degrees, for 3 billion years. You are touching the inside wall of a passage that was last touched by flowing lava before the first complex animals existed on Earth. The Cambrian explosion, the event approximately 538 million years ago, during which the basic body plans of almost all modern animal phyla appeared in the fossil record, occurred 2.5 billion years after this rock solidified. The first fish appeared roughly 500 million years ago. The first tetrapods, the first vertebrates to walk on land, appeared approximately 375 million years ago. The first mammals appeared approximately 225 million years ago. All of that happened after this rock was already old. You pull your hand back and continue deeper into the passage. The floor of the cave is relatively smooth, smoother than the surface above, protected from the micrometeorite rain by the ceiling above it. Small patches of fine regolith have accumulated in low spots, sifted down from the ceiling over the long millennia, but most of the floor is the bare basalt of the original tube floor. Your boots make no sound as they press against it. They leave impressions in the thin dust patches. The impressions will remain. You have walked approximately 40 meters from the entrance. Your helmet lamp beam reaches the walls and ceiling clearly, but the passage ahead continues into darkness beyond it. The radar data from the LRO showed the cave conduit extending at least tens of meters from the entrance, the confirmed minimum, but radar imaging from orbit can only see as far as its signal penetration allows, and the actual tube may extend far beyond what any instrument has yet measured. The 200-plus pits identified across the lunar surface by the LRO represent possible windows into a subsurface network whose full scale remains unmapped. Some of those pits are separated by only tens of kilometers. Whether they connect, whether the passages beneath the mare form a linked system or isolated individual tubes, is a question that has never been answered, because no mission has ever entered one. Until now. The passage widens further as you move deeper. At 60 meters from the entrance, the walls are perhaps 10 meters apart at the widest point, and the ceiling has risen to approximately 5 meters above the floor. The geometry here reflects a zone where the original lava flow was most vigorous, where the highest volume of molten rock channeled through the tube during the eruption, carving the passage wider as the thermal energy of the flowing lava kept the walls from solidifying fully. The tube is its own record of the eruption that made it, narrower where the flow was slower or thinner, wider where it was deepest and most powerful. The architecture of the passage a direct map of the lava's behavior billions of years ago. You stop and look at the ceiling. In the beam of your lamp, the ceiling surface shows a texture that is subtly different from the walls. It is smoother in large patches, the original top surface of the lava flow, the surface that faced upward and cooled first, forming the crust under which the lava channeled. In these smooth patches, you can see a faint sheen in the lamp's light, a glassy quality produced by the rapid quenching of the uppermost layer of basalt as it met the vacuum and cooled in seconds rather than minutes or hours. That glassy layer is called a selvage, a word borrowed from textile manufacturing, where it describes the finished edge of a woven fabric that prevents unraveling. In geology, it describes the chilled edge of an igneous body, the material that cooled fastest and therefore has the finest grain and the most glass. The selvage on this ceiling has been intact since the lava that formed it cooled approximately 3.5 billion years ago. On Earth, such surfaces would have been weathered, broken down by freeze-thaw cycles, by rain, by the biological activity of organisms that colonize rock surfaces and slowly dissolve them. Here, none of those processes exist. The surface has been exposed only to the vacuum of the cave's interior, which is no different chemically from the vacuum of space. It has not been rained on. It has not frozen and thawed. Nothing biological has touched it. It looks, in your lamp's beam, exactly as it looked when it formed. You move on. The passage makes a gradual curve to the left, not dramatic, not a sharp bend, but a slow arc that over the course of 20 meters shifts your direction perhaps 30 degrees. Lava tubes on Earth curve this way too, following the slight irregularities of the terrain over which the original flow traveled, bending around obstacles in the topography, or following the path of least resistance in the bedrock below. This curve is a record of what the surface of Mare Tranquillitatis looked like 3.5 billion years ago, before subsequent impacts and lava flows reshaped it, before the crater that formed the pit above you punched through the ceiling and changed everything about how this part of the tube relates to the surface above. Beyond the curve, the passage straightens again, and you stop. Approximately 15 meters ahead, in the outer range of your lamp's illumination, the floor of the passage drops away, not vertically, not a sudden pit, but a gradual descent, the floor angling downward at perhaps 10 to 15 degrees, continuing into the darkness below the beam's effective range. The lava that last flowed through this passage drained downslope in exactly this direction, leaving the tube floor tilted in the direction the molten rock moved as it evacuated. You walk to the edge of the downslope and look down. The darkness below is complete. Your lamp cannot reach the bottom of the descent. The passage continues downward and curves out of sight within 30 meters, and what lies beyond that curve has not been measured by any instrument that is yet operated on the moon. The temperature at your feet, registered by the suit's floor proximity sensor, is 17.1 degrees Celsius. This is worth staying with for a moment, this number and what it means. The surface of Mare Tranquillitatis above you right now is at approximately 120 degrees Celsius because the sun is illuminating it directly. In 14 Earth days, when the lunar night arrives, that same surface will cool to approximately negative 173 degrees Celsius. That swing will happen over the course of 2 weeks, a slow change by Earth standards, but a dramatic one in terms of its physical consequences for any material on that surface. The basalt of the surface cracks and fractures over geological time under this cycling. The regolith is churned and reprocessed. The chemistry of the surface is altered by the solar wind that arrives unimpeded during the day, bombarding the topmost layers with high-energy particles. None of that happens here. The cave's temperature has been approximately 17 degrees Celsius for as long as this space has been enclosed. Not exactly 17 degrees. The precise equilibrium temperature depends on the geometry of the cave, the thermal properties of the rock, and the minor heat from the moon's interior, but close to it, stable, varying by a fraction of a degree over the course of a lunar month. The physics behind this stability is the same physics that makes any enclosed space more thermally moderate than its exposed surroundings. The sun's radiation cannot enter the cave directly. The cave walls absorb the small amount of radiation that does enter from the pit opening and re-emit it, but because the cave is enclosed, that re-emitted radiation bounces between the walls rather than escaping into space, reaching an equilibrium that reflects the average of all the energy inputs rather than the peak of the daily solar maximum. And the interior of the moon, at the depths this cave reaches, contributes a small but steady heat flux, approximately 18 milliwatts per square meter, rising from below, that keeps the floor from ever getting as cold as the surface does during lunar night. The result is an environment that has maintained a temperature comfortable for an unprotected human being, though no unprotected human being has ever been here, or anywhere near here, for 3 billion years. 17 degrees. The temperature of a cool room on a mild day on Earth. Maintained by physics, without machines, without management, without anyone checking or adjusting. Just the geometry of an enclosed rock passage and the thermal equilibrium it reaches when insulated from the extremes above. You sit down on the sloping floor at the top of the descent. The cave is quiet around you. Your helmet lamp illuminates the curved walls of the passage, the layered basalt, the glassy ceiling selvage, the smooth floor descending ahead of you. Behind you, 40 meters back and then 45 meters up, the entrance to the pit is a distant pale gray rectangle of indirect light from the surface above. You are deeper inside the moon than any human being has ever been. The cave holds its temperature. The darkness beyond your lamp holds whatever it holds. More passage, more basalt layers, more of the geological record of a world that was once violently alive and has been quietly preserving that record ever since. You sit with that for a moment. The suit hums. The temperature is 17 degrees. The passage waits ahead of you, curved into the dark, patient in the way that only geology can be patient, indifferent to the question of when or whether anyone comes to see what it contains. You are here now. That is enough. You take a breath of the suit's recycled air, and you look deeper into the dark, where the passage curves out of sight and the lamp cannot follow, and you let the scale of what surrounds you, 3 billion years of geological stillness preserved at 17 degrees in a passage that has never been touched, settle into you the way silence settles when you finally stop resisting it. Slowly, without urgency. The cave is patient, and so are you. The descent begins gradually. The floor of the passage slopes downward at perhaps 10 to 15 degrees, not a dramatic angle, but enough that each step carries you measurably lower into the moon's interior. The basalt beneath your boots is solid, unweathered in the way that surface rock cannot be. On the lunar surface above you, micrometeorites arrive continuously, not in a storm, but in a slow statistical rain that over billions of years has battered the top centimeters of every exposed rock into the fine gray regolith that covers the entire lunar landscape. Down here, the ceiling intercepts nearly everything. The floor is protected. What you are walking on is basalt that has not been disturbed since the last lava drained through this passage 3.5 billion years ago. Your helmet lamp moves with you, illuminating the cone of space immediately ahead, while the rest of the passage holds its dark. At the outer edge of the lamp's beam, the walls are a deep absorptive gray, almost black in places where the basalt composition is richest in iron and titanium, slightly paler where the silica content is higher. Lunar mare basalt is not a uniform material. Over the hundreds of millions of years during which the mare plains were built up, eruption by eruption, flow by flow, the chemistry of the magma varied with each pulse. Different depths in the lunar mantle, different degrees of partial melting, different mixtures of the minerals that make up the mantle's composition. Each flow left behind a basalt with its own chemical fingerprint, its own ratio of iron to magnesium, its own titanium content, its own degree of crystallinity determined by how quickly it cooled. The walls of this passage record those variations in the banding you can see as you walk. Not dramatically, you would not notice it in a casual glance, the way you might notice the layering in a road cut on earth where sedimentary rock has been exposed. But under the focused beam of the lamp, the subtle differences in texture and slight tonal variation are visible at the boundaries between flows. A horizontal line of slightly finer grain, a zone of slightly darker material above a zone of slightly lighter. Each boundary is a moment in the volcanic history of the moon, the end of one eruption, a pause of unknown duration, and then the beginning of the next. You run your gloved hand along one of these boundaries as you walk. The texture changes under your fingertip sensors from slightly rougher above to slightly smoother below. The upper flow cooled more quickly at its base, where it met the already cool surface below it, producing a finer grain size at the contact zone. This is a feature that geologists on Earth call a chilled margin. It forms wherever magma meets a cooler surface and loses heat faster than the interior of the flow, producing a fine-grained or glassy zone at the contact that is chemically identical to the rest of the flow, but texturally distinct. This chilled margin formed 3.5 billion years ago, and the time between when this margin solidified and when you touched it just now, Earth's continents have moved from wherever they were in the Archean into their current positions and then rearranged again. The oceans have changed their chemistry multiple times. Life has evolved from single cells to multicellular organisms to the full complexity of the modern biosphere. Civilizations have risen and fallen. Human beings have learned to write, to build, to fly, to send spacecraft to other worlds. And this boundary in the basalt has been here in the dark at 17 degrees Celsius, unchanged. You are touching 3.5 billion years. You continue down. The passage widens further as the slope continues. At approximately 20 meters below your entry point into the main tunnel, the ceiling has risen to perhaps 7 or 8 meters above the floor, and the walls are far enough apart that your lamp beam cannot easily reach both sides simultaneously. You swing the light left, then right. The left wall is close enough to read clearly. The same layered basalt, the same dark texture, a section where the original lava tube wall has fractured along a vertical joint and left a clean face of fresh basalt exposed. The right wall is at the edge of the lamp's effective range, visible as a gray surface, but without the resolution to read its detail. This is a larger passage than the one you entered. Stop here for a moment and think about what the surface directly above you is experiencing right now, while you stand in the passage below it. The surface of Mare Tranquillitatis, the dark basalt plain that you walked across before finding the pit, is at approximately 120 degrees Celsius under the direct lunar sun. The solar radiation arrives at 1,360 watts per square meter, unfiltered by any atmosphere, heating the top millimeters of basalt to temperatures that would burn exposed skin in seconds. The solar wind, a stream of charged particles flowing outward from the sun, is striking the surface continuously, embedding hydrogen and helium ions into the topmost layer of regolith, altering the chemistry of the surface minerals through a process that has been operating without interruption for 4.5 billion years. Ultraviolet radiation, at wavelengths that Earth's ozone layer absorbs almost entirely before reaching the surface, is bombarding the mare rock directly. Over geological time, ultraviolet photons break chemical bonds in surface minerals and in any organic molecules that might arrive with meteorite material. The surface of the moon is, from a chemistry standpoint, an extraordinarily reactive environment, hostile to any compound that would be stable in a more sheltered setting. And then there are the micrometeorites. Every hour, the lunar surface receives impacts from particles ranging from submicron dust to centimeter-scale fragments, arriving at velocities of 10 to 70 kilometers per second. Each impact releases energy far out of proportion to the impactor's mass. A 1 millimeter fragment, arriving at 20 kilometers per second, carries the kinetic energy of a rifle bullet. The cumulative effect of this micrometeorite rain over geological time is the regolith that covers everything: the surface rock, shattered and reshattered, and ground and mixed, and sintered and melted and resolidified, processed into a complex layer that is simultaneously the most thoroughly destroyed surface material in the inner solar system, and paradoxically, one of the most scientifically information-rich. None of this happens here. The solar radiation stops at the basalt ceiling above you. The ultraviolet photons are absorbed within the first millimeters of rock they encounter. They cannot penetrate meters of basalt. The solar wind particles, charged and directional, are stopped by the rock and never reach the cave. The micrometeorites are intercepted. Their kinetic energy is absorbed by the ceiling, leaving small impact craters on the cave roof over geological time, but never reaching the walls and floor below. What you are walking through is, in the most literal physical sense, the opposite of the surface above. Every destructive process that has shaped the surface of the moon for 4.5 billion years stops at the boundary of this cave. The walls have not been solar wind processed. The floor has not been micrometeorite gardened. The chemistry of the basalt surfaces in this passage is, to a significant degree, the chemistry those surfaces had on the day they cooled from lava. This is the scientific treasure of a lunar lava tube. Not just that it is a potential shelter for human beings, but that it is a natural laboratory in which the history of the moon's volcanic past is preserved in a form that the exposed surface cannot offer. The surface has been processed, mixed, and altered. The cave interior has been protected. A sample of cave wall rock returned to Earth by a future mission would allow scientists to read the original chemistry of the Mare basalt directly, without the corrections and complications that lunar surface sample analysis requires to account for space weathering. The volatile content of the rock, the trace gases trapped in pore spaces during cooling, might still be measurable, providing information about the composition of the volcanic gases that accompanied the ancient eruptions. This is why planetary scientists have called for cave exploration missions for decades, and why the confirmation of an accessible cave beneath the Mare Tranquillitatis pit in 2024 was received not just as an engineering milestone, but as a scientific breakthrough. The caves are not just shelter, they are archives. Consider what the ceiling above you is doing right now as you walk through it. The lunar surface, the surface that is 105 meters above the pit entrance, and then some additional depth above this passage, is continuously exposed to two sources of radiation that Earth's surface is almost entirely shielded from. The first is solar energetic particles, high-energy protons and other charged particles accelerated by solar flares and coronal mass ejections from the sun, arriving at the moon without any magnetic field to deflect them and without any significant atmosphere to absorb them. During a major solar event, the particle flux at the lunar surface can be intense enough to deliver a radiation dose that would be dangerous to an unprotected human body over the course of hours. The second source is galactic cosmic rays, high-energy particles originating from sources outside the solar system, supernova remnants, active galactic nuclei, the energetic processes of the broader galaxy that arrive at the moon continuously and isotropically from all directions. These particles are extraordinarily energetic, and their interaction with the moon's surface rock produces secondary radiation through a process called spallation, in which the primary particle strikes an atomic nucleus in the basalt and fragments it, releasing a shower of secondary particles that penetrate deeper into the material. The surface of the moon, over the course of a single year, receives a radiation dose approximately 200 times higher than the annual dose received at Earth's surface. Over the course of a long-duration mission, weeks or months, this exposure would accumulate to levels that significantly increase cancer risk and could cause acute radiation sickness during extreme solar events. The ceiling above you changes all of this. Every meter of basalt that sits between you and the surface absorbs and scatters the incoming radiation. The density of basalt, approximately 3,000 kilograms per cubic meter, makes it an effective shield. The meters of rock above this passage do not eliminate the radiation environment inside the cave, but they reduce it dramatically. Studies of terrestrial analogs and lunar radiation models suggest that even a few meters of basalt overhead reduces the cosmic ray flux by an order of magnitude or more. Tens of meters of basalt, the depth at which this passage sits below the surface, reduces it further still. The cave is not perfectly radiation-free. Cosmic rays energetic enough to penetrate any practical thickness of rock still arrive. The rock itself contains trace amounts of radioactive elements, uranium, thorium, potassium-40, that contribute a small background dose. But the radiation environment inside this passage is a fraction of what it is on the surface above. An astronaut standing here, under the ceiling, would receive a radiation dose per hour that is dramatically lower than what their colleague, standing on the Mare surface above, would receive. This is not a small consideration. It is one of the central reasons why planetary scientists, mission planners, and human spaceflight researchers have been intensely interested in lunar lava tubes for decades. The challenge of long-duration human presence on the moon is not primarily one of life support. The technology for recycling air and water, for growing food in sealed environments, for managing the physical requirements of human biology and low gravity is within reach or already demonstrated. The challenge is radiation. There is no quick solution to the radiation problem on the lunar surface. You can build thick walls, but thick walls require mass, and mass must either be launched from Earth at enormous cost or manufactured from local materials in processes that have not yet been demonstrated at scale. You can go underground, but excavating rock on the moon with current technology is enormously difficult. Or you can find a space that is already underground, already shielded, already the right temperature. The lava tubes of the lunar Maria are the only known structures in the inner solar system outside of Earth that may naturally provide all three of those conditions simultaneously. The Marius Hills region, approximately 350 kilometers northwest of where the Mare Tranquillitatis pit sits on the surface above you, contains what may be the largest confirmed candidate for a lunar lava tube anywhere on the moon. Grail gravity data, analyzed in a study published in 2023, identified a mass deficit in the Marius Hills, consistent with a lava tube approximately 60 kilometers long, 9 kilometers wide, and 605 meters below the surface. 9 kilometers wide, a passage wider than many cities are long, holding its ceiling of basalt intact under the moon's low gravity, in darkness since the same volcanic period that formed the passage you are in now. You are in a small tube, a known tube, one that has been directly confirmed by radar. What the Marius Hills data suggests is that passages like this one are not isolated features of the lunar landscape. They are part of a broader system of subsurface architecture that the Mare volcanism built during its billions of years of activity, a hidden skeleton of empty space beneath the smooth, dark plains that cover the moon's near side, a network of passages whose full extent has never been mapped because no instrument has ever entered one from below. The Grail spacecraft, twin orbiters that flew in precise formation around the Moon between 2011 and 2012, measuring the gravitational field with enough resolution to detect the mass deficit created by a large underground void, found candidate lava tube signatures at multiple locations beneath the Maria, not just in Marius Hills, in Mare Tranquillitatis, in regions of Oceanus Procellarum. Wherever the Mare volcanism was extensive and the lava flows sustained, the conditions existed for tubes to form and for some fraction of them to survive intact through billions of years of geological time. The Moon's gravity is what makes this possible. On Earth, a lava tube 1 kilometer wide would collapse under the weight of the rock above it. The gravitational stress on a 1 kilometer span of basalt at Earth's surface gravity, 9.8 meters per second squared, exceeds the tensile strength of the rock. The sealing fails. The tube is destroyed. This is why the largest confirmed lava tube on Earth, Kazamura Cave in Hawaii, is approximately 20 meters wide at its widest point. 20 meters. On the Moon, structural stability analyses published in the journal Icarus show that a lava tube 1 kilometer wide can remain stable with a ceiling only 2 meters thick. The 1/6 gravity reduces the stress on the ceiling so dramatically that structures which would be geologically impossible on Earth are not only possible, but likely common on the Moon. The same analyses suggest that lava tubes up to 5 kilometers wide may be structurally stable under the right conditions, sufficient burial depth, the right roof thickness, the right initial stress state of the rock. 5 kilometers wide. A passage 5 kilometers across, maintained in basalt by nothing more than the Moon's low gravity and the structural properties of solidified volcanic rock. You walk through your passage, perhaps 10 meters wide, perhaps 8 meters high, and think about what 5 kilometers wide means. The city of Philadelphia, in a famous illustration produced to accompany the 2017 Grail gravity study, fits inside a theoretical cross-section of a maximum-size lunar lava tube, not uncomfortably, with room to spare. The cave you were in would fit inside that illustration like a single hallway fits inside a city block. The scale of what may exist beneath the lunar surface has never been directly measured. It has only been inferred from orbital data, from gravity anomalies and radar echoes, and the spatial distribution of surface pits. The instruments that have provided this inference are sophisticated, and the scientists who analyze the data are careful, but inference is not measurement. What actually exists in the darkness beneath the Maria, its true extent, its geometry, its structural integrity, its chemistry, is unknown to a degree that few places in the inner solar system can claim. You are in one of the few places that is that unknown. Every step you take adds to the total distance any instrument has penetrated into the lunar interior through an accessible passage. The slope levels off. The descent has brought you to a broader section of the passage, a zone where the lava tube expanded as the flow was at its most vigorous, where the highest volume of molten basalt channeled through and eroded the walls slightly outward over the duration of the eruption. The floor here is nearly flat, or flat enough that walking feels different from the careful downhill steps of the descent. You stop in the middle of the passage and turn off your helmet lamp. The darkness is immediate and absolute. Not the darkness of a room with the lights off, where your eyes gradually adjust and find shapes in the ambient light leaking under doors or through curtains. There is no ambient light here. There is no light of any wavelength reaching this section of the cave. The nearest sunlight is more than 100 meters above you and several meters to the east, filtered through the geometry of the pit above. It does not reach here, neither does starlight. The ceiling of basalt above you is meters thick, impenetrable to the wavelengths of visible light. You hold your hand up in front of your face. You cannot see it. Not dimly, not as a silhouette, not at all. This is what the interior of this passage has looked like for 3.5 billion years, for longer than any light has had the opportunity to enter. You stand in it for a moment. Your suit's life support hums. Your breathing continues. The temperature sensors read 17.2 degrees Celsius. Everything else is dark and silent in a way that has no comparison on Earth. Then you reactivate your lamp. The cave reappears. Walls, ceiling, floor, all exactly as they were, unchanged by the moment of darkness you introduced. The lamp's photons scatter off the basalt surfaces, and some fraction return to your eyes. This is the first time light has done this in this precise section of the passage. The photons reaching your eyes right now are the first photons to bounce off these particular square centimeters of wall since the lava that formed them solidified. You are the first source of light this space has ever had. The thought is not dramatic in the way it might seem if you said it quickly. It is simply a fact, and its weight arrives slowly as you stand in the cave and let it settle. Every shadow your lamp creates on the cave wall is a shadow that has never existed before. Every surface your light reveals has been waiting in the dark since it cooled. 3.5 billion years of waiting. You resume walking deeper into the passage. The cave continues beyond the flat section into another gradual curve. Your lamp has a range of perhaps 6 or 7 meters in which everything is clearly lit. Another 3 or 4 meters of dim illumination at the edge of the beam, and then darkness. The curve ahead takes the passage out of sight within 20 meters. You follow it. Beyond the curve, the passage opens into something different. The walls on both sides pull back, not gradually but noticeably, over the span of perhaps 5 meters, expanding the cross-section of the tube to perhaps 15 meters across. The ceiling rises to what your lamp's angle suggests is somewhere above 10 meters. You cannot see the full width of the passage from where you stand, and the ceiling is at the upper limit of the lamp's effective illumination. You are in a chamber. Not a perfectly defined room, not the kind of chamber that forms in a limestone cave on Earth, where water-dissolving calcite creates spaces with curved walls and elaborate speleothem formations. This is a volcanic chamber, formed by the dynamics of lava flow rather than chemical dissolution. Its shape is irregular, determined by the variations in how quickly different sections of the tube wall cooled, and how much thermal erosion the flowing lava did as it moved through. But it is distinctly larger than the passage on either side of it, and it has a different quality of space. In the beam of your lamp, you can see the far wall for the first time, a vertical face of layered basalt, approximately 15 meters distant, its surface showing the same flow stratigraphy as everywhere else in the passage, the same dark texture, the same faint horizontal banding at the boundaries between eruptions. Above the far wall, near the ceiling, there is a feature. A protrusion of basalt extends downward from the ceiling surface, not a stalactite in the carbonate sense, not a mineral deposit precipitated from water, a lavasicle. A structure formed when a small amount of still molten basalt dripped from the ceiling during the cooling of the tube and solidified before it could fall to the floor. It is perhaps 30 centimeters long, slightly tapered at the tip, dark gray like everything else in this cave. It has been hanging from that ceiling since the day it froze into place. 3.5 billion years of hanging, unchanged. There is a science to what this lavasicle represents beyond its simple existence as a geological curiosity. On Earth, speleothems, the stalactites and stalagmites and flowstones that form in limestone caves, are among the most useful archives that planetary scientists and paleoclimatologists have found for reconstructing past environments. Speleothems form from water saturated with dissolved calcium carbonate, and the rate at which they grow, the isotopic composition of the minerals they deposit, and the trace elements they incorporate all reflect the climate and environmental conditions at the time of formation. Ancient speleothems preserve records of temperature, rainfall, and atmospheric chemistry going back hundreds of thousands of years. The lavasicle above you is not a speleothem. It contains no water-deposited minerals, no isotopic climate signal, no biological trace. It is just cooled lava. But what it has preserved is different, and in some ways more valuable: the absolute physical absence of alteration. The lavasicle has not changed since it formed. No water has touched it. The moon has no liquid water, no rain, no groundwater, no hydrothermal fluids at the depths and temperatures of this cave. No wind has eroded it. No freeze-thaw cycle has fractured it. No biological organism has colonized its surface and slowly dissolved the mineral grains. It is the same object it was 3.5 billion years ago. This pristine preservation is one of the most scientifically compelling aspects of lunar cave environments. The surfaces inside a lava tube have been isolated from the processes that modify exposed lunar surfaces: solar wind bombardment, ultraviolet radiation, micrometeorite impacts, extreme thermal cycling. The minerals on the cave walls retain their original chemistry. The textures preserve the original details of how the lava flowed and cooled. Volatiles that may have been trapped in the pore spaces of the rock during cooling, gases from the eruption, trace elements from the magma, may still be present in concentrations that have been depleted to essentially zero on the exposed surface above. Studying a lunar lava tube wall is in this sense like reading a document that has been kept in a sealed vault since it was written. Everything that was true of the rock at the moment of formation is still there to be read. You walk slowly to the center of the chamber and stop. The silence here is different from the silence of the passage. In the passage, the walls were close enough that the sense of space was defined and contained. Here, the space is larger, and the silence fills it differently. Or rather, the silence is the same, but your perception of it changes with the geometry of the room. There is more space to be silent in, and somehow that makes the silence feel larger. You sit down on the cave floor. The basalt beneath you is flat enough to sit on comfortably, slightly cool through your suit's insulation. The temperature sensor reads 17 degrees even. Your lamp illuminates the chamber around you. Walls, ceiling, floor, the lavasicle hanging above the far wall, the dark openings of the passage behind you, and a continuation of the cave beyond the far wall, where the chamber narrows again into another passage. The cave continues. You do not know how far. The radar data from orbit established that the cave conduit exists and extends at least tens of meters from the pit above. The gravity anomaly data from Grail suggests mass deficits in this region consistent with a much larger system, but those are orbital measurements, statistical inferences, probabilities, what is in front of you, the passage beyond this chamber, the continuation of the tube deeper into the basalt, has never been measured by any instrument. It is simply unknown. And unknown in science is not the same as empty. Unknown means unvisited. It means the data has not yet been collected. It means that everything from an empty tunnel that extends 10 more meters and stops, to a passage that continues for kilometers through the volcanic interior of the moon, is equally consistent with what the instruments have told us. The not knowing is not a failure of science. It is the frontier. Consider what this chamber could become. The question of how human beings will live on the moon for extended periods, not days or weeks in a pressurized module landed from Earth, but months or years in a way that is sustainable and safe, is one of the central challenges of the next era of space exploration. The answer to the radiation problem, the thermal problem, and the micrometeorite problem might be standing in this chamber. A lava tube the size of this chamber, properly sealed at its entrances, could be pressurized with breathable air. Engineering simulations published in the journal Acta Astronautica demonstrated that a small lunar lava tube can maintain structural integrity under internal pressurization. The basalt walls, thick and strong, resist the outward pressure of the contained atmosphere without catastrophic failure. The same simulations suggested that lava tubes of this scale could sustain pressure differentials comparable to what is needed for human habitation. The thermal environment is already solved. 17 degrees, stable, no heating or cooling required beyond what the human body needs relative to a comfortable ambient. Compare this to a surface habitat where the thermal management system must handle the 300-degree daily swing, where insulation must be perfect and redundant and continuously maintained, and the cave's advantage is obvious. The radiation environment, as you have already moved through on your descent, is dramatically reduced compared to the surface. The basalt ceiling is a shield that costs nothing to maintain, requires no power to operate, and improves with depth. What remains is the air, the water, and the food. The air problem, maintaining a breathable atmosphere inside a sealed cave, is a challenge of engineering and logistics, not of physics. Oxygen can be extracted from lunar regolith through processes that have been studied and partially demonstrated. Carbon dioxide scrubbers are mature technology, carried on every crewed spacecraft for decades. The mass of air needed to fill a cave of this size is large, but it is a one-time investment rather than a continuous cost. The water problem connects back to the South Pole, to the ice deposits in the permanently shadowed craters, to the cold traps that have been accumulating water since before complex life existed on Earth. Water transported from the poles to a lava tube habitat would provide not only drinking water, but oxygen and hydrogen through electrolysis, oxygen for breathing, hydrogen for fuel. And the food problem, the hardest of the three, has been addressed in initial experiments that are still in their early stages. Plants have been grown in simulated lunar regolith, and the properties of enclosed cave environments, stable temperature, isolation from radiation, are in many respects more favorable for controlled agriculture than a surface greenhouse exposed to the lunar environment. The cave you are sitting in is not a habitat, not yet. It has no air, no water, no food, no sealed entrance, no lighting except your suit's lamp. It is a geological feature that formed 3.5 billion years ago and has been waiting since then in the dark at 17 degrees for something to arrive that would understand what it could become. You are what arrived. You are sitting in what may be the template for the first home that human beings build on another world. That thought is not small. Let it arrive at whatever pace it arrives at. It does not need to be hurried. Some thoughts are too large to absorb quickly, and the appropriate response to them is not to resolve them, but to simply sit with them while they settle into the parts of your mind that process large things slowly. The chamber is quiet around you. The lavasicle hangs above the far wall, unchanged. The passage continues beyond the far wall, deeper into the basalt, into the unknown extent of whatever this tube system is. But you are here, in this chamber, in this moment. And the cave does not require you to go any further. It does not require anything from you at all. It is simply here, as it has always been here, holding its temperature and its silence and its geological record in the dark. Let the weight of your body settle into the cave floor. Let the 17 degrees become the temperature of the world you are in right now. Not the temperature of a machine or a controlled system, but the temperature that physics has been quietly maintaining here for 3.5 billion years without any assistance. The equilibrium of an enclosed space in the lunar interior, balanced between the small heat flux rising from below and the cold vacuum that pulls heat from above, settled into the number that the geometry of this cave and the thermal properties of basalt produce when left alone for long enough. 17 degrees. The temperature at which a human body in normal conditions requires very little active effort to maintain its core temperature. The temperature of a cool, still room. The temperature this cave has been since before any animal walked on land, anywhere in the solar system. Let the silence stop being something you are aware of and become simply the condition of where you are. The cave holds. The temperature holds. And in the long patience of a space that has been waiting for 3.5 billion years, a few more minutes of stillness is nothing at all. The basalt walls hold their heat. The lavasicle holds its form. The darkness beyond the lamp holds everything it has always held. And you hold your position in the center of this chamber, breathing slowly, aware of where you are in a way that requires no additional words. Inside the moon, at 17 degrees, in the oldest shelter in the inner solar system, let your eyes close if they want to close. Let your body take the stillness the cave offers. It has been offering this stillness for 3.5 billion years. It does not mind sharing it tonight. There is a thought worth sitting with before the stillness completes itself. Human beings have been living in caves for a very long time. The archaeological record of human cave habitation extends back at least 300,000 years, to the Middle Stone Age in Africa, where cave sites like Blombos Cave on the South African coast contain evidence of human presence and behavior, engraved ochre, shell beads, the charcoal of ancient fires. Go further back in the hominid record, and cave use extends even longer, into the periods occupied by Homo erectus and our other ancestors, back through the Pleistocene ice ages, when caves provided the thermal insulation and physical protection that allowed hominids to survive winters in climates that would otherwise have been lethal. For most of human evolutionary history, A cave was not a curiosity or a destination. It was home. The physics that made caves valuable to early humans are the same physics that make the cave you are sitting in scientifically compelling as a potential future habitat. Thermal stability, the cave's natural insulation keeping the interior temperature moderate while the exterior temperature swings through extremes. Physical protection, the rock ceiling and walls blocking radiation, wind, micrometeorites, and whatever else the environment outside is doing. The sense of enclosure, the bounded space that is easier to heat, easier to seal, easier to make habitable than an open surface. In a lecture about lunar lava tubes, NASA scientist David Page noted, "Humans evolved living in caves, and to caves we might return when we live on the moon." The continuity in that observation runs in both directions. Human beings returning to caves is not regression. It is the application of an ancient and proven solution to a new set of physical constraints. The basalt ceiling above you performs the same fundamental function as the limestone overhang above a Neanderthal hearth 30,000 years ago. It separates the interior from the hostile exterior and makes the space within livable. The exterior conditions are different. The limestone overhang blocked rain and wind. The basalt ceiling above you blocks solar radiation, cosmic rays, and micrometeorites. The principles are identical. Protection through rock, warmth through enclosure, shelter through geology. You are sitting in what is simultaneously one of the oldest and one of the newest ideas in human history. Oldest because the cave as shelter predates writing, predates agriculture, predates everything we think of as civilization by hundreds of thousands of years. Newest because the specific cave you are in has never been inhabited, never been used, never been entered by any living thing in the 3.5 billion years of its existence, and the technology that would allow it to be inhabited does not yet exist, but is being developed, tested, designed, argued over in engineering meetings and scientific conferences on a planet 384,000 kilometers from where you are sitting. The cave is patient. It has waited 3.5 billion years already. A few more decades of human engineering are nothing. Let that patience become something you can feel in the rock beneath you, and the walls on either side of you, in the ceiling meters above your head. Not urgency, not pressure, not the pressing quality of something that needs to be resolved before you can rest. Just time. Vast, unrushed, geological time. The kind of time that does not notice a day's worries or an evening's restlessness. The kind of time that holds 3.5 billion years of volcanic history in a wall of basalt and barely registers that anything has happened. Let the scale of that time do what large scales do when you genuinely sit with them, not as an abstraction, not as a number read from a page, but as the actual quality of what is around you right now. The basalt walls are 3.5 billion years old. The silence has been complete since the lava drained. The temperature has been 17 degrees since before any eye in the solar system could see. And you are here, briefly, warm inside your suit, breathing recycled air, sitting on a floor that no one has sat on before. Let the brevity of that presence, the few minutes or hours of a single human being's attention in a space that has existed for longer than complex life, be exactly what it is, not diminishing, not overwhelming, just proportionate. You are small relative to the cave. The cave is small relative to the moon. The moon is small relative to the solar system. The solar system is small relative to the galaxy. And yet you are here, aware of all of it, in a way that the basalt cannot be, and the vacuum cannot be, and the 3.5 billion years of geological time cannot be. That awareness, specific, located, temporary, is something the cave has never had before. Hold it lightly. It does not require effort to hold. It simply is. The temperature is 17 degrees. The silence is complete. The cave continues deeper into the basalt, into the dark beyond the lamp, into the unknown extent of whatever this passage system is. And you are here, at the edge of the known, at the beginning of whatever comes next, in the oldest shelter in the inner solar system. Let your breathing slow. Let the 17 degrees be enough. Let the dark beyond the lamp be simply dark, not threatening, not empty, but full of basalt and time and the long patience of a world that was once alive with fire and has been quietly preserving its record ever since. The cave holds. The temperature holds. And the silence holds, as it has held since before the Cambrian, as it will hold long after tonight. You are held inside it, gently, without condition, for as long as you need. The lamp can stay on or go off. You have that choice here in the chamber in a way that almost nowhere else you have ever been has given you so cleanly. On the surface above, the sun provides light whether you want it or not. There is no switch for the solar constant, no way to dim the unfiltered radiation of a star from 150 million kilometers away. In a city on Earth, the ambient light of civilization bleeds through every window and curtain, the orange glow of streetlights and the blue wash of screens making true darkness an effort rather than a default. In the average room on Earth, the darkness at night is never complete. Here you have a lamp that runs on batteries and a cave that has been in absolute darkness for 3.5 billion years. The choice is real. You turn the lamp off. The darkness arrives the same way it arrived before, immediately, completely, without gradation. One moment there is light and the chamber is visible. The next moment the light is gone and the chamber is gone, replaced by a darkness so total it is indistinguishable from the darkness behind closed eyes. The basalt walls are there, a meter or two on each side, but you cannot see them. The ceiling is above you, but you cannot see it. The lavasicle is hanging above the far wall, but you cannot see it. The passage continues beyond the chamber in both directions, but you cannot see them. You sit in the dark. The suit hums. The temperature sensor reads 17 degrees. Your breathing continues. And there is nothing else to register because there is nothing else happening in this space. No wind to carry a sound, no movement of any kind, no creature, no machine, no natural process anywhere in this chamber that would produce a detectable signal of any kind. The silence here is not the silence of a paused room, waiting for something to resume. It is the silence of a space where nothing has ever needed to resume, because nothing was ever going on. The cave did not pause when you entered, and will not resume when you leave. It simply continues to be what it has been, a passage in the basalt, at 17 degrees, in the dark, exactly as it was before you came, and exactly as it will be after. Your presence is the temporary thing. The cave is the permanent thing. That inversion, the human visitor, as the transient element in an environment that predates human existence by 3.5 billion years, is worth sitting in the dark with. On Earth, it is easy to feel the opposite. Humans have reshaped the surface of an entire planet. The concentration of carbon dioxide in Earth's atmosphere has increased by nearly 50% since the Industrial Revolution, a geological change that is happening at a rate with no natural precedent in the last 66 million years. Satellites orbit the planet in their thousands. Radio waves from Earth's broadcasts have been traveling outward at the speed of light for over a century, expanding in a sphere now more than 100 light years in radius. The evidence of human activity is so pervasive on Earth that geologists have proposed naming a new geological epoch after it, the Anthropocene. None of that has reached this chamber. The electromagnetic radiation expanding from Earth's broadcasts passes through this cave the same way it passes through any rock, attenuated by the basalt, absorbed within a few meters. The carbon dioxide concentration in Earth's atmosphere is irrelevant here because there is no atmosphere here. The satellites are in orbit far above. The Industrial Revolution has had no effect on the temperature of this cave, which has been 17 degrees since before there were hominids, since before there were mammals, since before there were dinosaurs. You are inside the one place on the moon, perhaps one of the few places in the accessible solar system, where the signature of human civilization is exactly 0. The rock around you is unchanged. The temperature is unchanged. The silence is unchanged. The darkness is unchanged. You have been here, and your presence will leave no lasting mark. The impressions your boots made in the thin dust on the cave floor will remain for a very long time. There is no wind here, no water, no process that would erase them, but the dust itself was already there. The cave was already there. The basalt was already there, and all of it will still be there long after the boots and the suit and the person inside them have returned to the surface and eventually to Earth. The cave does not notice you. It holds you anyway. Not through intention. A cave has no intentions. Not through care, in any sense that implies awareness, but through physics, through the geometry of enclosed space, and the thermal properties of basalt, and the specific temperature that results from those properties when left alone for long enough. The cave holds 17 degrees. You are 17 degrees from any point within it. The temperature is the shelter. Let that be the last scientific fact you hold tonight before the words stop and the stillness takes over. Not the most dramatic fact, not the 9-kilometer-wide lava tube under Marius Hills, not the 300 million square meter potential of the lunar subsurface, not the city of Philadelphia fitting inside a theoretical cross-section of the maximum possible tube. Those are extraordinary. They belong to the daylight side of this story, to the part of it that involves planning and engineering and the long human project of extending its reach. This is the nighttime side. 17 degrees. In the dark, in the quiet, in a chamber that formed when the moon's interior was still hot enough to produce flowing lava and has been cooling ever since toward the equilibrium it now holds. The moon's interior is not entirely cold. The radioactive elements at depth, uranium, thorium, potassium-40, still decay, still produce heat, still send a small flux of thermal energy upward through the rock toward the surface. The total heat flow from the lunar interior is approximately 18 milliwatts per square meter, a tiny fraction of what Earth's interior produces, a tiny fraction of what the sun delivers to the lunar surface in daylight. But it is real, and it is one of the inputs that determines the equilibrium temperature of this cave. The moon is still generating heat. Not enough to power anything, not enough to produce volcanism, not enough to be felt in any direct physical sense, but enough to contribute to the 17 degrees, enough to prevent the cave from ever reaching the cold of the lunar night surface, enough to mean that this temperature is not just a historical coincidence, but a current dynamic equilibrium, a balance between the heat flowing up from below and the cold radiating down from the vacuum above, reaching a stable point that has not significantly changed in hundreds of millions of years. You are sitting at the equilibrium point of the moon's thermal balance. The heat from 3.5 billion years of slow radioactive decay, rising through kilometers of basalt, reaching this chamber and being radiated away into the rock above, finding its balance, and the result is 17 degrees. The temperature of a cool, calm room. The temperature at which a human body, in normal conditions, is comfortable. The temperature at which sleep comes more easily than at extremes. Not through design, not because the moon arranged itself for human habitation, but because physics, applied without intention over geological time, produced this number in this space, and the number happens to be one that suits a warm-blooded organism from the third planet. Let the coincidence of that, if it is a coincidence which the probability theory of large numbers suggests it might simply be, settle into you without requiring resolution. There is a specific reason why cool temperatures favor sleep, and it is worth understanding before the words stop and the stillness takes over, because understanding it makes it easier to let it happen rather than resist it. The human body's transition from wakefulness to sleep is not simply a matter of lying down and closing eyes. It is a precisely orchestrated cascade of physiological changes, many of which are thermal. In the hours before sleep, the body's core temperature begins to fall. Blood vessels in the skin dilate, allowing heat to radiate away from the body's surface. The hands and feet warm slightly as blood flow to the extremities increases and the core cools. This drop in core temperature, typically about 1 degree Celsius over the course of an evening, is not incidental to sleep. It is a prerequisite. The brain requires this cooling to initiate and sustain the slow-wave sleep that constitutes the most restorative phase of the sleep cycle. The mechanisms behind this requirement involve the preoptic area of the hypothalamus, a small cluster of neurons in the base of the brain that functions as the body's primary thermostat and sleep regulator simultaneously. These neurons are sensitive to both temperature and the accumulation of adenosine, a chemical byproduct of neuronal activity that builds up during wakefulness. When the preoptic area detects the right combination of falling temperature and rising adenosine, it initiates sleep by suppressing the arousal systems of the brain, the locus coeruleus, the tuberomammillary nucleus, the dorsal raphe, and activating the sleep-promoting systems that produce slow, large amplitude electrical oscillations in the cortex. The cooling of the cave helps you. Not because the cave is cold, 17 degrees is comfortable, not cold, but because a comfortable ambient temperature, slightly below body temperature, naturally facilitates the heat dissipation that your body's thermoregulatory system needs to perform. A room at 17 degrees draws heat from the body's surface, gently and continuously, supporting the core cooling that the hypothalamus is trying to achieve. The body does not have to work to lose heat. The cave provides exactly the gradient that allows it to happen without effort. 3.5 billion years of physics, arriving at precisely the temperature a sleeping mammal requires. Consider what the surface above you is doing to the bodies of any creatures that might theoretically be there. The 120-degree daytime surface temperature would rapidly overheat any warm-blooded animal not protected by an elaborate thermal management system. The negative 173 degrees of lunar night would freeze tissue in minutes. No biological system that evolved on Earth for Earth's conditions could survive unprotected on the lunar surface for any length of time. The cave is different. The cave is, by the accident of orbital mechanics, volcanic history, and the thermal properties of basalt, exactly the kind of place a biological organism could occupy without extraordinary technological intervention. Not today, not without a pressure suit to provide the breathable atmosphere that the cave lacks, but in terms of temperature, in terms of radiation, in terms of the basic physical conditions that make a space survivable, the lunar lava tube is closer to habitable than any other place in the inner solar system outside of Earth itself. That is an extraordinary fact. Not inspiring in a vague way, specifically extraordinary in that the probability of a natural geological feature on another world having the right thermal properties for human habitation is not high, and yet here it is, a passage in the basalt of the moon at 17 degrees, maintained without machinery, without power, without any human intervention, by physics alone. Let your breathing slow now. Not as a technique, not as a practice that requires attention or effort, just as the natural consequence of a body that has been carrying the weight of a day, any day, the specific day you came from before this night, and has now been still long enough, in a quiet enough place, that the waking tension in the muscles begins to soften on its own. The cave floor is not uncomfortable. The temperature is 17 degrees. The darkness, with the lamp off, is complete, and complete darkness is one of the most favorable conditions for the kind of sleep that a body, after a long day, most needs. Not the fitful half-sleep of a bright or noisy environment, but the deep restorative sleep that biology has optimized for over hundreds of millions of years of evolution in environments where night was genuinely dark. The ancestors of every animal alive today evolved in darkness. The lunar cave is dark in a way that almost no natural environment on Earth still is. Not threatening dark, not the dark of danger or confusion, the dark of geological patience, the dark of a space that has been exactly this way since before the first animal developed the ability to perceive light at all. Let your body recognize this dark for what it is. Not absence. Presence. The presence of the cave walls, the basalt ceiling, the floor beneath you. The presence of the moon itself, a world that was once alive and has been quietly holding its record in the dark for 3.5 billion years, and is holding you now in the same dark at the same temperature with the same geological patience it has always had. You do not need to do anything with that. You do not need to think about it, or understand it, or resolve it into a conclusion. You can simply let it be the ground you rest on. The cave floor beneath you, the basalt walls on either side, the ceiling above, meters of ancient rock, protecting you from everything the lunar surface above it is experiencing right now. The solar radiation, the micrometeorites, the temperature that has already begun to shift as the geometry of the lunar day continues. None of that is here. Here is 17 degrees. Here is quiet. Here is dark. Here is 3.5 billion years of uninterrupted stillness, briefly interrupted by you, and already returning to stillness around you as you sit and breathe and let your weight settle into the stone. The cave does not need you to stay awake. It has been here without you for longer than you can meaningfully imagine, and it will be here after, and your wakefulness or your sleep makes no difference to the 17 degrees, or the silence or the dark. So let it go. Let the wakefulness go the way the lamp went when you turned it off, not gradually, not with effort, but simply by removing the thing that was maintaining it. The cave is patient. It will hold you through the night. Whatever the night requires, the deep, slow breathing of genuine rest, the stillness of a body that has released the day, the long quiet of hours in the dark. The cave has been holding these things since before the night had a name. Let sleep come, not as something you chase or accomplish, as something that finds you in the dark and the quiet and the 17 degrees. The way it has always found the creatures who came to rest in caves. The way it has always found living things when they finally stopped moving and let the dark be what the dark is. Let it find you now. The lamp is off. The temperature holds at 17 degrees. The chamber is quiet. The basalt is old. The moon is out there, turning slowly, its surface swinging between extremes that this cave will never feel. And you are inside it, warm, still, in the oldest shelter that exists within reach of a spacecraft, in the dark that has been here since before the Cambrian. At 17 degrees, which is the temperature physics produces when it is left alone long enough in a cave on the moon. Let your eyes be still. Let your hands be still. Let your breath be slow and even, the way breath becomes when the body knows it is safe and the mind has stopped looking for reasons it might not be. The cave holds. The temperature holds. The dark holds, and you are held inside all three of them in the quietest place a human being has ever rested, in the oldest shelter in the inner solar system. The surface of the moon tonight is swinging through its extremes, the Terminator line creeping slowly across the Mare, the sunlit rock at 120 degrees, and the shadowed rock falling toward the cold that makes Shackleton's floor look almost warm by comparison. None of that is in the cave. None of it has ever been in the cave. The cave has its 17 degrees, and its silence and its dark, and it keeps them the way basalt keeps everything, without preference, without effort, without any awareness that it is doing something remarkable. It is just physics. Just the equilibrium of enclosed space on the moon. Just 3.5 billion years of staying exactly this way. Let that be enough. Let the day you came from be smaller now than it was when you began. Not gone, it is still yours, still real, still waiting for you in the morning with whatever it was carrying, but smaller, measured against the walls of this cave and the age of this basalt and the patience of a world that was born in fire and has been cooling quietly ever since. The contents of one human evening are proportionate and manageable and not urgently in need of resolution tonight. Tonight, the cave holds them along with everything else, lightly, without judgment, at 17 degrees, Think about what the cave has held before tonight. Not in a human sense. The cave has held no memories, no histories, no records of previous visitors, because there have been no previous visitors. But in a geological sense, the cave has held its own history in its walls and floor and ceiling since the day it formed. The layered basalt on the walls holds the record of eruptions and coolings that span hundreds of millions of years of the moon's volcanic life. The composition of each layer carries the chemistry of the mantle at the moment of that specific eruption, the mixture of iron and magnesium and titanium and silicon that tells a geochemist exactly what depth the magma came from and what minerals were melting at that depth. The grain size of each layer tells you how quickly it cooled. The texture of the contact zones between layers tells you how much time passed between one eruption and the next. All of this is written in rock, in the dark, in the silence, waiting for the instruments that can read it. The floor holds the record of everything that has fallen through the pit above since the pit opened. Micrometeorite dust accumulated over millions of years, the rare chemical signal of a distant volcanic eruption on Earth carried upward into the atmosphere and eventually lost to space, but perhaps in trace amounts captured in the electrostatic regolith of the pit floor. The floor is a slow, fine-grained diary. The ceiling holds the record of what has been above it, the history of the lava tube's formation preserved in the selvage glass, the lavasicle recording the exact moment the last drip of molten rock refused to fall and froze into its permanent form. 3.5 billion years of record, in a space that will not lose it, in the dark that preserves it, at 17 degrees that holds it steady. You are sitting inside the archive. Not reading it, that requires instruments you do not have with you tonight, an analysis that takes months in laboratories on a distant planet, but sitting inside it, surrounded by it, enclosed in it in the most literal physical sense. The cave walls are within reach of your outstretched hand. The ceiling is a few meters above your head. The floor is the surface you are sitting on. The archive is not abstract here, it is immediate. It is the rock you touched earlier, the lavasicle hanging above the far wall, the faint layering visible at the edge of the lamp's beam. It is the oldest room you have ever been in, and the temperature is 17 degrees, and the silence is total, and the dark with the lamp off is as complete as dark can be. Let all of it be the context of the rest you are taking now. Not something to think about actively, not a problem to solve or a topic to fully explore, just the context, the background, the room you are in as you let the day's effort release from your body and the night do what night is for. Your spine can soften now. The muscles that have been holding posture since morning can release into whatever surface supports you, the cave floor in the story, the mattress or pillow or couch in the room where your body actually is. Your jaw can be loose. Your hands can be open. Your feet can be still. The moon is out there, and the cave is in it, and the cave is at 17 degrees in the dark, and you are resting in the fact of all of that. The suit hums. The temperature holds. The cave has been here for 3.5 billion years, and it will be here tomorrow, and it will be here long after any human being's concerns have resolved themselves one way or another. It does not rush. It does not require anything of you. It simply holds its 17 degrees and its silence and its dark as it has always held them, as it will always hold them. And you, briefly, warmly, alive in a way the cave has never been alive, are resting inside that holding. Let the rest be complete. Let the dark be enough. Let the 17 degrees be the temperature of the place you are going now, the quiet place where the body does its overnight work and the mind releases its grip on the day. The cave holds, and you are held. Sleep well. Everything you heard tonight is real. The cave is out there right now, beneath the mare, at 17 degrees in the dark. If this story found you tonight, if the cave and the dark and the 17 degrees gave you somewhere to rest, consider leaving a like or subscribing to Quiet Science at Bedtime, or turning on the notification bell so the next story reaches you. These episodes take care to build, and every gesture of support makes the next one possible. Good night.